Hello, my name is Jack Lee, and I will be presenting the first part of this presentation from Lab 7.
Loudon, and I will be presenting parts B and C, measuring wavelengths and the wavelength separation of a sodium doublet for Lab 7 for the Optics Lab 380A, while Jack will be presenting part A, the configuration factor.
So beginning with part A, we aligned the Heaney laser with the interferometer just to make sure that it was hitting the center of the mirrors. Next, we aligned the interferometer. We were able to do this so that we could see the spot on a card coming out of the interferometer, and it was blinking and kind of hazy, and we could actually see some of the interference patterns on the card. We next added a lens. This allowed us to fine tune because now we're able to see an actual spot. You'll see more of that in the next slide. We then moved the micrometer and we were able to count 100 fringe cycles, and we saw the difference in the micrometer movement. And using this, we were able to calculate the configuration factor using the equation on the right side there. And this configuration factor will allow us to figure out how much the actual mirror is moving with respect to how much we move the micrometer, because they're not a one-to-one relation. And as you can see here, we found that the conversion factor is 2.15. We did this twice, as you can see in the data there at the bottom. We got very similar results with both.
Video, Loudon is cycling through the 100 bright fringes of the Heaney laser, which allowed us to calculate the configuration factor of the micrometer. In this part of the lab, we used the same procedure as in part A, but we were required to find the wavelength of the three different sources: a mercury source, a Heaney laser, and a sodium source. Using the equation on the right, which relates the wavelength of the source to the inverse relationship between the change in micrometer distance and the change in fringes, we were able to find the wavelength of the laser diode to be 651.4 nanometers, the mercury source to be 558.4 nanometers, and the sodium source to be 595.6 nanometers, which, as you can see in the percent error table below, was very close to the expected value of sources. Consequently, we can conclude that our experimental procedure was thoroughly conducted. In this video, you can see Jack cycling through the bright fringes of the provided mercury source. Using the change in micrometer distance of 50 fringe modulations, we are able to calculate the wavelength of the mercury source. In the lab, we were required to use the sodium source in conjunction with the Michelson interferometer to define the change of wavelength between two primary wavelengths being emitted. Therefore, after properly aligning the interferometer, we adjusted the micrometer to the end of its scale and then found the first instance of no visible fringe modulation. Then, by adjusting the micrometer, we found 3 more instances of no visible fringe modulation, and then used the square of the wavelength of the sodium source that we found earlier in the lab, divided by the average modulation spacing of the 4 null spaces to find the difference between the two wavelengths being emitted. Ultimately, we found the difference to be 5.4 angstroms, which is very close to the actual separation of 6 angstroms.